So good morning students. Today we are going to see about the basic planar process. It consists of 7 steps. Already 9 steps. Already we have discussed about the silicon wafer preparation. So that was the most important step. It's a silicon wafer preparation. The most commonly used, the Cholesky process was used for the silicon wafer preparation. The second comes, it's a epitaxial growth. So in this epitaxial growth, the Greek word epi meaning, it's a Greek word, it's an epi meaning upon, and the past tense of the word tinian. It's for your taxial, arranged. So in this condition, you are going to arrange the silicon crystal wafers in a proper order. So it's this epitaxial growth is a thin layer we are going to fabricate over this silicon wafer preparation. So earlier we might have seen as P substrate. So above this we are going to make it as an N thin layer. This we call it as an N epitaxial layer. So here this process is carried out in a reaction chamber with a long cylindrical tube. So here in this reaction chamber, the silicon wafers are arranged in an order, and the graphite boat, this graphite table, we call it as a boat. And this is surrounded by an RF induction coil. These black surroundings, we call it as an RF induction coil. So in this we are going to pass gases. So here the gases like nitrogen, the hydrogen with silicon tetrachloride. So we are going to diffuse some impurities. So here we have two types of impurities to be added, are N-type and P-type impurities. So the N-type impurities are phosphine. So in general we call it as a phosphorus, and for your P-type we use a material called boron. So here in for this combination of this boron, we call it as a biboron, the silicon tetrachloride or the phosphine PH3, H2 plus PH3 can be passed through this gas. Then we are going to get an outlet in the case of your silicon wafer. So in this we are going to use a chemical reaction, that is, for example, a silicon tetrachloride with an hydrogen on the temperature to be maintained in this for an inductive coil is 1200 degrees centigrade. We are getting a silicon as an outlet and with a hydrochloric acid. So in this epitaxial we are going to grow an N-type thin layer over the P substrate. That is the concept. It's placed in a reaction chamber. The silicon wafers are arranged in a quartz crucible similar to a Cholesky's process, and this heated with an temperature of 1200 degrees centigrade is surrounded by an RF induction coil, and gases are to be passed from this. So this gases may be N-type and P-type impurities to be added. Okay, so next come oxidation. That was your third step in the basic planar process, whereas the epitaxial is the second process. Now this process. So in this oxidation, we are going to prevent the impurities, okay, into the epitaxial layer. Preventing, that means we are going to stop diffusing the impurities. So in this oxidation, we might have studied in our chemistry that we have then adding the oxygen, that is addition of oxygen is another way called as oxidation. So in this we are going to make it as an N layer. Already we have mentioned it's a P substrate. In this we are going to develop an N epi layer, that is your epitaxial layer. Then over this we are going to make it as an SiO2 layer. This is going to prevent the diffusion of impurities towards the N epitaxial layer. So in this we are going to do the oxidation process. Similarly, this oxidation process is also done with a hot furnace So the temperature is to be maintained in the range of 950 degrees centigrades to 1115 degrees centigrades. So here the SiO2 is a hard protective agent. So it's an which is unaffected by almost all other chemical reagents except hydrofluoric acid. So the hydrofluoric acid is the only acid to be used to remove the silicon dioxide. So here, as I said earlier, so this will be reacted, the silicon plus the to H2O on reaction gives the silicon oxide, dioxide plus 2H2. So this is a hard protective layer. Hot protective layer, and it is almost react with all the chemical reactions except hydrofluoric acid, which removes all the next comes the photolithography. That was your fourth topic to be discussed in this basic planar process, and the very important process is called as the photolithography. So in this photolithography technique, the conventional technique uses UV light exposure. So here the dimensions of to be reduced for less than 2 micrometer. That's the only thing, the device dimensions. Why we have to go for the photolithography? So here we are going to design a pattern based on your circuits to produce a small device. So that we are going to pass an UV light exposure in the conventional technology, whereas the latest technology uses X-ray or electron beam technology. So these are the both technologies to be used, and we prefer UV light exposure in the conventional method. So here the X-ray technology is less than 1 micrometer, less than or equal to 1 micrometer dimensions. So in this photolithography, as the name itself mentioned, that we are going to pass some light to remove some agents, as oxidizing agents. So here we use a main term called the masking and etching. These are the two major process, masking and etching. So this masking, whichever the area which are not to be removed, so we are going to protect with a layer called as masking. Then whichever the area to be removed with the help of some acids, as I said earlier. So SiO2 is a protective agent with the diffusion of impurities. Even though we need wherever somewhere we require some impurities to be diffused, so in that condition we are going to pour some acids to remove that silicon dioxide to be removed. For that we prefer a hydrofluoric acid. So in that condition the etching process plays a major role. So in this we are going to see with the 4 concepts how the silicon P substrate, N substrate, then SiO2 layer. This is our SiO2 layer to be used, which are the process to be removed and which are the layers to be protected. So in this, the first we have 4 diagrams. In this we have a silicon wafer, over that we have an SiO2 layer, then we are going to apply a photoresist film. So in this was the concept, we are going to apply a photoresist film. Next comes, we are going to pass a UV light exposure. So here I have followed a conventional method called UV light exposure. So in this, above the silicon wafer we have an oxidizing agent SiO2 layer, then we apply a photoresist as such. In your first diagram is came as such. Then we are going to pass some UV light ultraviolet radiations. So here I don't want to remove such portions, so I am going to mask something that is covered in this black shade. This we call it as a photo mask. Then we the rest other areas we are going to apply UV light radiations. So next comes here the third picture. So in this the photo mask are to be removed. Okay, so here these other polymerized photoresist are to be left over. Okay, in this again I want to remove the silicon dioxide layer. So in the silicon dioxide layers are to be removed by hydrofluoric acid. This is the process we call it as a etching. So in this here, the silicon wafer, over that we had an SiO2 layer. Now in this picture we have an SiO2 layer. Now we remove this SiO2 layer with the with the hydrofluoric acid. So here an etching process takes place. Okay, so in this we have two methods, the UV light exposure and the X-ray electron beam technologies. So in this UV light exposure, as I mentioned, the order dimensions to be reduced to 2 micrometers. In this latest technology, the X-ray electron beam technology is used only for the shorter wavelengths, and the cost wise it is expensive when compared to your UV light exposure. So and the process the time taken for this complete process is lesser in UV light exposure when compared to the X-ray or electron beam lithographic technique. So this electron beam lithographic technique is used when the application specific applications with the dimensions to be less than 1 micrometer, and especially this cost is effective. So next comes the fifth technology called as the diffusion. So in this diffusion we have the diffusion is nothing but the addition of impurities. As I said earlier, the oxidation, the SiO2 layer is used to prevent the impurities not going beyond this N epi layer or to the P substrate, whereas the diffusion layer, so we all know that a pure gold is not used for an ornament, so we have to add some materials like a copper. So it's like adding impurity to make an ornament. So in that, like that, we are going to diffuse some impurities. So as I mentioned earlier, we are going to diffuse N type and P type impurities. Similar to that, we are going to add this impurities. So in this, while diffusing the impurities, it should go beyond to the silicon wafers. So in this diffusion concept, it is maintained in the high temperature furnace. So in this high temperature, we are going to take a 20 cleaned wafers. Already we are going to make we are making in the process of silicon wafer, those that we are making a 20 cleaned wafers to be taken, and it's put it in the hot zone with the temperature maintained at 1000 degrees centigrade. Temperature to be maintained at 1000 degrees centigrade. So it's a heated process taken place. In that condition, we have to add some impurities. So the impurities to be added are boron oxide. So in general, it's used as boron, and it is as phosphorus, as I mentioned. For P-type impurities, it is for phosphorus. So we can add the boron oxide or boron chloride in terms of your boron, whereas for phosphorus we can add phosphorus pentaoxide P2O5 and phosphorus oxychloride POCl3. So here we have an expression that we are going to add some impurities. So this to be maintained at high temperature. To maintain this at a high temperature, a hydrogen gas, a dry oxygen or nitrogen gas to be maintained, to be passed to this impurities. This we call it as a carrier gas. So next comes an ion implantation. That was your sixth process in ion implantation. So far we have seen the epitaxial growth, oxidation, photolithography, then diffusion. These are temperature dependent techniques, whereas the ion implantation is like an high voltage ions. It's an like a bombardment of ions to be taken place when compared to the temperature. So here the ion implantation again. So here the adding of impurities, here again in inserting we are impurities to a particular location where we have to insert. So here we have a diagram. Look at this diagram. So here we have a mass separation electromagnet. So here, as we all know, that mass separation is like a weight, which are the ions which comes under this to a range of higher range, that to be passed, whereas the less weightages were to be removed. So here this taken place in a vacuum chamber. So in this place we are going to place some ions. That ions will given a high voltage power supply, those to be forwarded through the mass separation electromagnet, where the acceleration ions takes place with an electron volts in the range of 20 kilovolt to 250 kilovolt. So these ions travel in this energy with the 20 kilovolts to 250 kilovolts. It may pass through the Y deflection plates and the X deflection plate. This is similar to your cathode ray oscilloscope operation. Then it strikes your silicon wafer. So this silicon wafer is our target chamber. We are going to pass some impurities, that may be your ions, that to be passed to the mass electron separation electromagnet, where this ions are forwarded to with a high voltage power supply. So in this the acceleration takes place, then it hits the silicon wafer. Then it's maintained that usually we don't have a temperature. Here we are performed at low temperatures, and it is maintained in the with the help of the high voltage power supply and the acceleration electrode, whereas the diffusion takes place in the furnace, the quartz tube to be arranged and high temperature to be maintained. This is the only difference. Here the temperature to be maintained, here it's placed in a vacuum chamber, and the high voltage power supply is to be given as the energy to be accelerated. Okay. So the next topic towards the ion implantation is the isolation process. So here a number of components to be fabricated in this region. So we have two types of techniques called p-n junction isolation and dielectric isolation. So in this p-n junction isolation, we are as the name itself terms that explains that isolation is nothing but your separation process. So here we have two types, as I mentioned, p-n junction and dielectric. So here the capacitor, we have a capacitor, we call it as a parallel plate, and it uses a dielectric medium, that may be a mica, ceramic, paper, like that is an example for your dielectric. So here first we are going to look into the p-n junction isolation. So here usually we start with a p substrate, that is our silicon wafer. Over that we provide an epitaxial layer. So here we are going to do a p-n junction isolation. So in this p-n junction isolation, we are going to separate the island. So separation, so here we are going to insert a p plus higher ions to be and it is separated by an epitaxial layer. So this region we call it as an isolation island, this n epitaxy. So here I have made it as a 4n epi layer. So 4 components with 4 different islands are to be made. So now here we call it as this. We have connected a diode at the two back to p-n junction diode back to back. So here this it's like anode side, and here it's anode side, the other end is like a cathode. Now I have taken a common point, in that I am giving a substrate as a negative. So here if I connect anode to the negative, so usually we have a p-n junction diode, we have two biasing regions. One is the forward bias region, the other one is the reverse bias region. So here the positive of the battery is connected to the anode terminal and the cathode is connected to the negative terminal of the region. We call it as a forward bias. So in this condition, the substrate is nothing but your negative terminal of the battery. Similar to that, it's connected to the negative, it is connected to the anode. So in this condition, the diode works in the reverse biased region. This makes the separation, and this forms an isolation island. So next comes the dielectric isolation. So isolation is nothing but your separation. So in terms of the dielectric medium, so here we are going to place a p substrate. Between your p substrate and an epitaxial layer, we are going to introduce a thick layer called dielectric layer. So here it's a P substrate. Over that we are going to make an N-epi collector. It's an N-epitaxial layer. Over that we are going to make a P-type component, P-type impurities to be introduced. Then we are going to diffuse the impurities, and these things are to be like the metallization concept to be introduced. This we discuss about later. So here we are going to discuss only about the dielectric isolation. This is a separation between your P substrate and N epitaxial layer. So in between we use a thick film epitaxial layer. This same operation is done in case of your PNP or NPN transistor. So this dielectric medium we use silicon oxide or the ruby. So these are the materials to be used to separate your P substrate and N epitaxial layer, and this operation of your PNP or NPN transistor is same as your dielectric isolation. So in this concept, this dielectric isolation is applied for this transistor is very expensive, and it's mainly used in military purpose and the aerospace laboratories. So these are the special isolation techniques used in your ICs, or mainly used in aerospace or military applications. Next comes metallization. So over this we have placed the P substrate, N epitaxial layer, then we have made an oxidizing agent, we can diffuse some impurities. If doesn't want, we have to remove the impurities using the concepts of masking and etching. Then we are going to do ions to be passed, which strikes your silicon wafers. Next comes the metallization. So metallization is nothing but you are giving interconnections to the components. So here the metallization uses aluminum as the most important metal. Okay, so here this metal, the preferred metal is a good conductor, and it has a good bonding between the silicon wafers. Okay, so next comes the metallization. So here this metallization, this operation to be focused in the vacuum chamber. So we are using a vacuum chamber. In this, the evaporant source, we are using a metal that to be heated to extreme temperatures, that to be heated, and these things are to be vaporized and evaporated, which it hits the substrate. So everything directions to be in a straight line, which it hits the substrate and it condenses to form a thin metal film. So those thin metal film is used for the interconnections. So this is the concept to be done in metallization. So we are going to heat that metal to be evaporated. So that evaporated to be processed in a straight line that hits your substrate, the condensed material to be made it as a thin metal film for the interconnections. So here they use a preferred material called aluminum. Okay. So the next process and the last process is the assembly, processing and packaging. So here, so for the metallization concept is done. So in this assembly, processing and packaging, we are going to make as a single wafers. So we have produced thousands of wafers in a single chip, or 10,000, what are maybe the, according to the wafer size, we are going to create a bulk ICs. So those things are to be separated, that to be tested, and we are going to process it with a we are going to verify all those things, parameters, then we are going to pack it. So here in this we have three different package configurations. One thing is metal can package, ceramic flat package and dual inline packages. So here the metal can packages, here the chip size will be like a small one. It will be very small in size, that to be made it in case of your metal thing. So we have the leads. See, the metal can package, ceramic flat package and dual flat package. The early method we have the metal can package. Here we have a metal can that to be placed over the top of your integrated circuit. It should prevent from any damages, and this may have 8 or 10 or 16 leads for the design of your integrated circuits that to be soldered and placed over the caps are placed over your integrated circuits. The ceramic flat package and dual in package are more or less similar, and the ceramic flat package is very costly when compared to the dual inline package, where in our laboratory purposes we follow a dual inline packages, and this may be like a plastic molded cover at the top, plastic molded. Okay.